we'll start. Hello, everyone. It's my great pleasure to welcome Professor Cynthia Chang from McGill University back to U of T. She has visited before, but it's her first time visiting as newly minted faculty, I believe. So, and we also have Jonathan Sievers in the back corner, her colleague, also professor at McGill. Yeah, like me, Cynthia is an experimentalist by training, and I first came across her name as a lead author on the paper publishing the first sort of constraint on primordial B-mode polarization from, the tensor to scalar ratio from primordial B-mode polarization with CMB alone. That's the bicep 1 measurement. After achieving that in grad school, she took on a prestigious Dickey Fellowship, I believe, at Princeton University, where she was instrumental, no pun intended, in developing the cryogenic system and receivers for SPIDER, balloon-borne CMB polarimeter. As you know, I worked on SPIDER as well, so we were colleagues, and we're on the ice together. And a funny anecdote, Cynthia actually saved SPIDER by performing last-minute, very delicate surgery, soldering together a broken wire that was creating a short in the windings of a motor. That was what allowed the telescopes to scan back and forth across the sky. And very careful thought was given as to who would be given that task. By then, she had already moved on to a position at the University of KwaZulu-Natal in Durban, South Africa, and turned her attention to longer wavelengths, specifically H1 intensity mapping. Today, she's here to talk to us not so much about intensity mapping, but more like detection of an overall intensity level, using a very novel and surprisingly simple experiment that hopefully can tell us a lot about the early epochs of the universe. So without any further ado, please welcome Cynthia Chang.
Cool. All right, well, thanks, Jamil, and thanks, everyone, for hosting me. It's really wonderful to be back in Toronto. So today I'm going to talk about this new experiment called PRIZM that we kickstarted in South Africa when I was at the University of KwaZulu-Natal. So I just moved to McGill a few months ago and hoping to keep this experiment running. So to set the scientific context for my talk today, I'm going to start off with the obligatory picture of the universe as we currently understand it. And this is drawn from an observer's perspective. So the limit of our observations is set by the formation of the microwave background, which represents the outer surface of this drawing. And as we all know, the microwave background has been a tremendous source of information on cosmological parameters and our understanding of the universe, but that literally scratches the surface of this picture, and there's a huge amount of cosmological volume between us and the surface of less scattering that still has a lot of mysteries yet to be explored. So shortly after the formation of the microwave background, the universe was a dark and boring place for a long period of time, so aptly named the Dark Ages. There was nothing but neutral hydrogen. And then as time went on, the first luminous objects ignited. So that's the period known as cosmic dawn. And then as these objects continued to evolve, eventually full-on reionization began to take place in the universe. And then later on in time, structures began to form. And then in recent history, there was dark energy that kicked in. And there's all sorts of strange and wonderful things that are to be explored in this picture. And so I actually work on a number of experiments that are trying to fill in the slices of the history here. But for today's talk, I will only talk about one of these experiments. So that is PRIZM, and it is focusing on this slice of the universe that is centered around cosmic dawn. So trying to understand the nature of the first luminous objects turning on in the universe. So our observational weapon for studying these slices of the universe is redshifted 21 centimeter emission from neutral hydrogen. So as everybody knows, hydrogen is a proton and electron, and they've got spins associated with them. And because of the hyperfine transition, the hydrogen atom occasionally emits a 21 centimeter photon. And that corresponds to the difference in energy states when the hydrogen atom transitions from the state where the spins are parallel to each other to the spins being anti-parallel. And so because this is fairly narrow emission, this is a great redshift tracer, and hydrogen is the most abundant element in the universe. So the upshot is that if you tune your radio telescope to the particular frequency that you're interested in, you can literally dial into the particular slice of the universe's history that you want to study. So that's the game plan for mapping out cosmic dawn. So generally speaking, with redshifted 21 centimeter experiments, there's two broad classes of measurements that people are trying to make. So these are fluctuation experiments versus global measurements. So I'm going to talk a little bit, just in broad detail, or broad strokes, about the difference between these two styles of measurements. In order to describe that, I'm going to start by drawing an analogy with the microwave background. So when people think of the microwave background, you normally think of these beautiful temperature anisotropies and polarization anisotropies that have been mapped out in exquisite detail by satellites such as WMAP and Planck. But we should remind ourselves that before these fluctuation measurements existed, the very first original measurements by experiments like Kobe and Firass were looking at the globally averaged or monopole signal for the microwave background. And looking at the intensity as a function of frequency. And that turned out to be a very important and complementary measurement to the fluctuations because these measurements showed that the universe is a perfect black body. So that spectral information holds a lot of interesting and important information about the thermal history of the universe that is distinct from the information that we get from the temperature fluctuations. So by taking these two measurements together, you can learn very different things about the universe's history and its nature. So a similar analogy exists in the world of 21 centimeter cosmology. So a lot of experiments out there, like the largest radio arrays, are focusing on measuring the spatial fluctuations and in fact trying to reconstruct that information in 3 dimensions. So these are experiments such as Hera, LOFAR, Chang, Hyrax, all across different redshift ranges. And these experiments are trying to do 21 centimeter tomography. So looking at the fluctuations as a function of angular scale and also as a function of redshift on the sky. So reconstructing these 3-dimensional cubes. But in the 21 centimeter world, there is also a very small number of experiments that's looking, again, at the globally averaged or the monopole signal as a function of frequency. And so that's these experiments on the right-hand side. The reason why this is scientifically interesting to us is that if you look at the globally averaged monopole signal as a function of frequency, that basically acts as a thermometer for us that can probe heating processes and energy injection in the early universe. So again, we can kind of trace out the thermal history, and that gives us information that's complementary to the fluctuation experiments. So for the rest of this talk, I'm going to focus on these globally averaged experiments and not talk about the fluctuations. But if anyone wants to talk about that later, I'd be happy to. Okay, so let me tell you a little bit about the thing that we're trying to measure when we're doing globally averaged experiments. The thing is this expression at the top. That's the brightness temperature. And this is a simplified expression that I have shown up here. So there's a factor that depends on the neutral hydrogen fraction. There's a redshift factor. And the most important part is this piece over here, which is that we are looking at the spin temperature of the neutral gas relative to the temperature of the microwave background. And the spin temperature in this case just tells you something about the fraction of the neutral hydrogen atoms that are in the energetically higher spin parallel state relative to the spin anti-parallel state. So that's it. But it is a relative quantity, so T sub s minus T CMB. And so the overall brightness temperature can fluctuate positive and negative in this graph below. So this is a representative model curve that shows you what we generally expect for this brightness temperature. So that's the amplitude on the vertical axis as a function of frequency going from left to the right, or equivalently cosmic time. So you can see in this model that there's a number of dips and features and wiggles, and anytime you see an interesting feature in a model curve, you know that there's some interesting physics behind it. So what I'm going to do is walk through this graph from the left to the right and try to explain just in a few minutes where these features come from. So on the very left-hand side, that corresponds to the earliest time right after recombination. So that's during the dark ages when the universe was dark and boring and just full of neutral hydrogen. So during this time, the universe is expanding, and the kinetic temperature of the gas is dropping in accordance with the expansion. And at first, there are collisions between the neutral hydrogen atoms that are very effective at coupling the spin temperature to the kinetic temperature. So the upshot is that at the beginning of this curve, you can see the brightness temperature dropping as the spin temperature tracks the kinetic temperature, and both drop together. Now, as the expansion of the universe continues on, eventually collisional coupling becomes ineffective at coupling the spin temperature to the kinetic temperature. So the kinetic temperature continues to drop, but the spin temperature decouples and drifts back up to the temperature of the CMB, and so that's why you see this turnaround at the very beginning of the graph. And in the absence of star formation or anything else happening, that would be the end of the picture. So you would see this little dip at the beginning, and then the curve would flatline, and that would be it. But as we go on in time, we think that the first stars form around here or so, and that dramatically changes the picture because those first stars inject extra photons into the mix. So in particular, we think that the first stars inject Lyman alpha photons into the universe, and those have the effect of bringing the spin temperature and the kinetic temperature of the hydrogen back into tight coupling via the Wolff-Hsin field mechanism. And so the upshot is that since the kinetic temperature has been dropping this entire time, when you inject these Lyman alpha photons and they bring the spin temperature back into coupling with the kinetic temperature, the spin temperature snaps down. So you see the sharp absorption feature from the spin temperature dropping back down to the kinetic temperature. Then as time goes on, we think that there's extra heating by gamma rays and X-rays from the first sources, and those are expected to eventually drive the kinetic temperature of the gas back above the temperature of the CMB, so the spin temperature tracks that as well, and we see the absorption feature turn around and go into emission instead. And then finally, full-on reionization begins, and that has the effect of depleting the neutral hydrogen supply. So then you start to see that this signal starts to get erased, and then by the time reionization is finished, we've flatlined and we're back down to zero. So in a nutshell, that's broadly speaking what governs the features behind this model curve. And of course, this is just one representative model. Yeah, question?
What are the biggest contributors to X-rays and gamma rays?
So I am not an expert on this, but so yeah, the details of this depend very much on what you assume about the population of the first luminous objects. So I can show you this picture, which is, this is an example of the parameter space that is spanned by these model predictions. And this is from Cohen et al. 2017. So you can see there's a lot of variations in what the models predict. And this is just one particular parameter that he's tuning here. So this is the ratio of the Lyman alpha intensity to X-ray heating rate. So broadly speaking, you can see that when this ratio is low, so the kind of more yellow curves, then the dip is less pronounced. It's kind of in the upper left, or yeah, the upper left. And then when this ratio is high, then you get more of a broad peak structure, or broad dip feature. But this is just one example, and this shows you the very broad spectrum of models that are out there. And of course, I think every theorist has their own prediction for what this signal should look like, depending on what other things, like you can throw cosmic strings into the mix if you want to as well. There's all sorts of ways to predict how this signal moves around. From an experimentalist point of view, if we measure this, then that should give us a lot of detailed information on how to constrain the model predictions.
Before you have considerable heating from the galaxy, then you're bounded by the temperature of the CMB and the temperature of matter, right?
That's right, yeah.
So the variation that we see here, are all the models bounded by the same? Because then
I believe so, yeah. I don't remember the details of this paper, but I think there's no extra exotic physics put in here. Yeah. But I'll have one other plot to show in a bit. So, so anyway, that's that. Yeah.
Can you explain why I assume it's photons that are close to ionizing hydrogen lowers the brightness temperature, but higher energy photons don't? I mean, what's the physics behind the dip from Lyman alpha photons versus not a dip from X-ray photons?
Right. So actually, I forget the exact explanation for this.
So what happens there is that you have a photon with a lot of energy, and it's much larger than the spin temperature. So all spin temperature is encoded on the difference between the photoionization energy. So all the photon does is a mediator. So the problem is that you have matter, and you can't transfer energy to the spin very efficiently. So all the photon does is transfer energy kinetic energy from the gas to the spin, and it's a small amount carried on top of the amount that you need to ionize the atom.
Yeah.
I think I get it.
Okay.
Right, you can remind me of the details of this afterwards as well. So yeah, I'm not an expert on the theoretical part of this, so that brings me to my next slide, which is the experimentalist perspective on this, which is why I like this plot. And the reason why this is a fun signature to search for is because, first of all, there's a distinctive feature in this, so that's always nice, because at least you have a prayer of separating it from systematic effects. It is difficult, but at least there's a non-zero chance of being able to do this. The frequency range range is also very accessible in some sense. The appropriate frequency range that brackets this signal is roughly 51 to 150 megahertz, give or take or so. So the good news there is that everybody can build a receiver in these frequency range. It's not that difficult. Of course, the downside I'll get to in a second. And then in the absence of systematic error, so if you just ignore that, from a statistical perspective, all you need is a few days of integration time to get this signal. But of course, there's a lot of fine print associated with that. So that brings me to my next slide, which is that so this is the fine print, and these are the 4 prongs of the skull and crossbones that really cause problems for our measurements. So I'll go through these one at a time. The first is that we don't just have the cosmological signal, we live in our galaxy, and so the foregrounds are a huge problem for us. And the important thing to notice on this picture is the color scale. And so the brightness of the foregrounds kind of lives in the 1,000 to 10,000 Kelvin range, depending on where you're looking. So that's 4 or 5 orders of magnitude brighter than the expected signal. The other thing that's bright that's hard to get away from is radio frequency interference, RFI. And so in those frequencies that I mentioned, 50 to 150 megahertz, that is right in the FM band. And so it's pretty hard to run away from that emission from most locations on Earth. The ionosphere also creates problems for us, so it attenuates and refracts the signal. This plot here is from the MWA, from a really nice paper by Chris Jordan. And what this shows is a map of the total electron count for, I think, a particularly bad ionospheric weather day. So you can see that there's fluctuations in that across the field of view. And these little arrows on there represent the amount of movement that sources are shifted by, just because of the phase. So anyway, the upshot is that the ionosphere refracts the signal and shuffles things around. So that's an additional source.
What are the units in the bottom right?
Oh, you mean the color scale?
Yeah.
I actually do not remember. So yeah, I'll have to look up the paper again. Sorry about that. So the ionosphere causes problems, and then of course the instrument is a potential source of problems as well if you don't understand it or if it's not spectrally smooth. So this is just one example from a paper by Rich Bradley where he analyzed some ground screen effects and showed that you can get some resonant behavior that can potentially introduce spectral features like this thing that looks very much like the dip that I showed in the cosmological model. So if you're not careful with the instrument, you can trick yourself into thinking that you see something on the sky when it's really just a feature of the instrument instead. So
suppose we were trying to build a monitor for the ionosphere. What's the time scale for it to look completely different?
Oh, actually, I don't know the time scales. I think it's discussed in his paper because, yeah, they do regular monitoring and they also separate the ionospheric weather into 4 different categories. So I specifically picked the worst example here, but there are certainly nicer days. So I think the MWA approach is to focus on the days where the ionosphere is quiet and then analyze that data and then just chuck out ones where it's like this. So.
Is there any significant atmospheric difference or, positional difference?
Right, not so much hemispherical difference, but there is latitude difference. So near polar latitudes generally have quieter ionospheric behavior.
South Atlantic anomaly weather probably is bad.
That's probably bad, yeah. yeah. Right, but polar and near polar latitudes, especially at night, are very nice and quiet. Okay, so despite the experimental challenges, this doesn't stop us from trying. And so I believe this is all of us that exist trying to do this measurement. So it's not very many of us. EDGES is the pioneering experiment that really developed this field. And they've been around for over 10 years now. So they've really made a lot of progress in understanding these kinds of measurements. And I think the only others that are operational or soon to be operational are LIDA, that's operating from the Owens Valley. There's the Cosmic Twilight Polarimeter that will soon be deployed to Green Bank. And then there's CERES-2, most recently CERES-3 actually, which just finished its most recent observing run in India. And you can see that all of these are in remote-ish locations to try to escape from the RFI. So let me mention EDGES for 1 second because they have made a name for themselves in the news because of this detection that they published earlier this year. So they've been doing this experiment for a while, and what they found was that most recently they have reported a detection of an absorption feature centered at 78 megahertz. So this is a plot from their paper. You can see that there is this absorption feature they have found. The different colored lines correspond to different instrumental configurations. I won't get into the details, but basically no matter how they change their instrument around, the signal persists. And so as far as they can tell, it is real in the sense that they haven't been able to identify any obvious instrumental effect. So it's something on the sky. Whether or not it's cosmological or not remains to be seen. So the main source of uncertainty or worry is pointed out in their abstract here, which says that the profile is largely consistent with expectations for the 21 centimeter signal induced by early stars. However, the best fitting amplitude of the profile is more than a factor of 2 greater than the largest predictions. So there are some oddities about this signal and their detection that people are still trying to sort out. So let's focus in on this a little bit more and talk about the features of the detection. So this is a really nice plot from Jordan Maraca, who's a CITA National Fellow at McGill, and he has a good paper summarizing an assessment of the edges detection. So you can see that the range of edges measurements is kind of in this gray band here. And if you take the default model in publicly available codes like 21 centimeter fast, that's this yellow curve, and that looks very different from the range of edges measurements that are allowed. And the problem is even worse when you consider the maximum bound for the absorption feature, because that's just set by the cooling of the universe and the expansion. So that's this dashed line here. And that sets a pretty hard lower limit for how deep the absorption trough can be. And you can see that edges plummets way past that. So there's 3 features that theoretically inclined people have been focusing on to interpret this signal, which is, first of all, how can we amplify the amplitude of this signal by a factor of 2 or 3? There's also a question of why the signal is centered at 78 megahertz. And then the shape is also a little bit funny because it's got a flattened bottom to it. So these are things that people have been thinking about. I'm not an expert on all of these, but I'll just say a few words about the amplitude, which is that if you go back to the expression for the brightness temperature, there's only a few mathematical knobs on the right-hand side that you can turn in order to make that amplitude deeper for the absorption. So there's 3 things that I've highlighted here. So the first is that you can make this term bigger so that it's overall more negative, right? And to do that, you've got 2 options. You can either increase the numerator or you can decrease the denominator. So if you decrease the denominator, that's decreasing the spin temperature. There are people who have proposed mechanisms for this via, for example, interactions between baryons and dark matter. And again, I'm not an expert on this, but these people are. So look up their papers if you're interested. You can also increase the numerator by cranking up the radiation background or the temperature of the CMB, something to inject extra radiation into the picture. So there have been proposals for dark matter decay or synchrotron from black holes and first galaxies. So again, there's a whole slew of papers describing these potential mechanisms. The other possibility is to alter the cosmology by changing these prefactors up front. So people have tried that as well. And then for a nice discussion of the timing of the signal and the shape, I recommend this paper by Jordan and Steve Furlanetto. So the quick summary of that is if you take the most basic galaxy evolution models, those tend to predict a signal that's centered at 100 megahertz rather than 78 megahertz. And then and you can try to either match the position of the dip or the width, but it's difficult to do both at the same time. So again, this paper has a much more detailed discussion of that. The upshot is that it's pretty difficult to explain theoretically what's going on with this detection. The EDGES team themselves, their own words are that they're agnostic about the interpretation and that they really want to see an independent confirmation. So that's quoted from the Nature paper, which is, although we have performed many tests to be confident that the observed profile is from a global absorption, we still see confirmation observations from other instruments. So that's what we are going to try to do, is weigh in on the detection and see if we see something similar. So this is the experimental effort that I'm involved in. So the experiment is a new one called PRIZM. It stands for Probing Radio Intensity at High Z from Marian. Just a little bit of history about this experiment is that it's the successor to the Sci-Hi experiment, for those of you who have followed the field and who've heard of it before. And that experiment was born out of Jeff Peterson's lab in Carnegie Mellon. And then the hardware literally moved to the University of KwaZulu-Natal a few years ago. And then we started rebuilding all of the hardware to make it more robust and to clean things up a little bit. And then we changed the name at that point because the old hardware is sitting in a scrap pile in the corner of the lab now. So it's all brand new hardware. And then just as of a couple of months ago, we moved to McGill. And along the way, we've picked up a number of collaborators in Berkeley and also across South Africa.
What's the language below KwaZulu-Natal?
That's isiZulu.
So that's how you're really supposed to say KwaZulu?
Yeah, I suppose so. I don't know the language. So. Yeah, that part, yeah. Okay, so I'll start off with an overview photo of the experiment. This is PRIZM installed at its site. So we have 2 antennas operating. They're at central frequencies of 70 megahertz and 100 megahertz. And then that's our command module over here with the electronics. So I'll go through all the components one step at a time. This is a schematic just to show you what was in the previous picture. And this is basically the simplest radiometer that you could imagine building. There's not a whole lot of parts associated with this. So for a single polarization, we have the antenna up front, and then the signal is fed into a mechanical switch that allows us to select between the sky signal and a number of calibrators on board. So we have a 50 and 100 ohm terminator. There's a short, and there's a noise source that we just installed earlier this year. There's a couple of levels of amplification and power distribution for all these components. And then all of this lives directly underneath the antenna, as I'll show you in a couple of more slides. And then there's a long run of coaxial cable to separate our back-end electronics physically from the front end to help reduce self-generated RFI. So in the back end, we have a few more levels of filtering and amplification. And then we use a snapboard for the readout and the digitizing. And everything is powered off 12-volt batteries, and there's regulated power for everything. So I'll walk you through, I'll give you a virtual tour of the instrument, one component at a time, following the signal chain. So starting off with the antennas at the very front end, we use modified 4-square antennas. This is a design that was inherited from Sci-Hi. And this improbable shape arises from FICO simulations that were run to optimize the beam structure and to minimize structure and variation within our frequency range. So these 2 antennas are scaled versions of each other to operate at the 2 central frequencies. And if I remember correctly, there's about 20 megahertz of overlap between the antennas. So they should be able to see the common signal in that frequency range where they overlap each other. Just to give you a sense of how the antennas operate, these are simulated beam patterns. Yeah? What controls the bandwidth? Just the details of the exact width of the petals. So I wouldn't be able to give you a quantitative answer because that all comes from the simulations. Basically, I mean, these are just cross dipoles. So in the one limit, if you have just a thin dipole, that's very narrow band. And so by widening it and making these kind of diamond shapes, that makes it more broadband. How to translate that into numbers comes from simulations, but that's the general idea. So these are the beam patterns. The top pictures show 2D beam plots at the central frequencies for these antennas. And then at the bottom, these are 3 dB and 10 dB contours in the solid and the dashed lines, respectively, at multiple frequencies. So you can see that there's some variation between the frequencies, but overall, it varies rather smoothly. So that's the antenna. And then moving down the chain, this is the front-end electronics, and you can see they physically sit underneath the antennas, and we can get to them through these access panels on the side. So this is a zoom-in of the front end, and it looks kind of like a mess, but basically what happens is the antenna signal is fed into the mechanical switch here. There are a few calibrators on board. It's pretty hard to see. This is the noise source on the left-hand side, and that's coupled into the mechanical switch. These are the 2 LNAs that we use, the low noise amplifiers, to boost the signal. And then there's regulated power connections running everywhere. There's also a whole bunch of temperature sensors popped in all over the place. So here's one, here's another one. Basically everything where we can monitor the temperature, we slap on a sensor. And then the amplified signal comes out the connections at the bottom. And there's a long run of coax to go to our back end. So this is what the back end electronics looks like. We have a Faraday cage that houses our readout boards. So we use snap boards for our readout. We'll come back to that in a second. We also have our second stage amplifiers in here and various housekeeping electronics for controlling the switches and for reading temperatures and doing a few other things. So let me just show you the snap boards really quick. So this is what we use for reading out. So we have an external ADC that talks to our snap board, and the ADC samples at 500 megasamples per second. The snap board, this is Casper hardware, and we program the FPGA with spectrometer firmware so that it's just taking spectra over and over again, autos and cross between the 2 inputs. And the spectra live between 0 and 250 megahertz, and we've got 4096 channels, so 61 kilohertz of resolution. The control for the snap board is achieved with this Raspberry Pi, so it's very simple to operate. All you have to do is SSH in and then do all your commands. And because it's very low data rate, we're just saving 4096 channels of spectral data to disk once every few seconds. We can dump all the data to an SD card on the Pi, so we have a very small, we have the small data problem as opposed to a big data problem. So the reason why the snapboards are nice, well, there's a number of reasons, but they're very low power consumption. So if you add up everything together, so both antennas, front ends and back ends, everything that you see in the picture, the whole system draws about 65 watts of power total. And so we have 8 huge batteries that we keep on site, 200 amp hours apiece. And so when the batteries are fully charged, we can run both antennas for about a week or so. In practice, it's a little less than that because the batteries aren't fully charged, but it does give us a decent amount of runtime. Okay, so that's the instrument in a nutshell. And this is a quick slide showing just what on-site operations are like. So this is our command module over here, and that's where the snapboards and the readout electronics are housed, and the cables run out the side to our antennas. And then for power, there's this hamster tube that we've installed between the 2 containers. So that runs power cables from our generator over to our battery. So there's chargers living in there. And then over here is our cache of fuel. We've got 500 liters stored in jerry cans. And a whole bunch of spares out there. So this is all we have on site. This is everything that we need to operate our experiment. And this is a view of our command module, just to see, just show you what it's like working out on site. So that's our huge battery bank. That's our back-end electronics. There's actually another system that we just installed this April. I'll come back to that later on. This is the wiring harness for the batteries. This is the chargers for the batteries. That's charging for the humans. And this is a space for us to work in. And then the mice are a problem. We'll come back to that later on. Another fun fact is that we've arranged the open side along with the prevailing wind so that when you're sitting in here, it's not too uncomfortable. It's a little bit cold, but it's all right.
So those are like lead-acid batteries?
Yeah, they're deep cycle, yep. And sealed and very nice. Okay, so let me tell you a little bit about the site that we're operating from. So this experiment operates from Marion Island, which is in the middle of nowhere. So it's here about halfway between South Africa and Antarctica. And this is a base that's operated by the South African National Antarctic Program. So we are 2,000 kilometers away from anything else. It's a very, very radio quiet location. PRIZM was actually the first astronomy experiment to be operated from this island. Traditionally, the base has been used for biology and geology research, so penguin counters and seal counters, and we're the first people looking up instead of around or down. So PRIZM it's a fairly new experiment. We did an engineering run in 2016 and kind of scoped out the island and the terrain. And then 2017 was the first semi-permanent installation of the antennas, and we've been doing science operations since then. So we're a little less than 2 years old. So with new sites come new challenges, and these are the primary ones that we face. So the biggest challenge is that access is only once per year to the island, so that's in April. And during every access window, we have 3 weeks to do everything that we want to do on site. So that includes unpacking, setting up, robustifying, everything. The island is situated in the roaring 40s, which means that the weather is really lovely all the time. So it's cold and windy and rainy and miserable, but we do it for the science. Also, the terrain is pretty rugged on the island, so getting around, you have to go by foot, and there's mires and lava rocks that you have to navigate. And finally, of course, there's mice. So they are an invasive species, and they are everywhere on the island. They really love to eat electronics. So they like electrical tape, self-amalgamating tape, heat shrink tubing, you name it. Anything soft and squishy that they can fill their stomachs with, they will try to eat. So it took us a while to figure out how to deal with that, but we did manage to win in the end. So we have managed to overcome both the weather and the mice, and the experiment is running okay at the moment.
Should I introduce some cats?
Huh? So actually, yes, they did introduce cats a long time ago, and then the cats discovered that eating the baby birds was a lot easier than eating the mice. And so then they had to bring in cat hunters, and they actually went out with rifles to get all the cats. So all the cats are gone now, but the mice are still there, unfortunately. Okay, so let me tell you about how we selected our site. The base is on the northeast corner of the island, and the island's pretty small, so it's about 25 kilometers across. And in order to select a suitable site for our antennas, we had to balance a few considerations. So first of all, we wanted a distance that's close enough to the main base that we could access it regularly. But on the other hand, you want to be far enough from the main base so that when people are playing on their laptops and their phones, that we don't see any RFI from that. So if you look at the terrain around the main base, there's a pretty obvious place to go, this is the largest hill around, so that's Junior's Cup. And if you go around the backside, it turns out the terrain there is pretty flat and workable and not full of mires. There's mires along the way, but not along the backside. So that's where we decided to site our experiment. It's about 4 kilometers from the base, so about an hour's commute one way every day. And when we were surveying that location, we were lucky that the helicopters were flying and slinging cargo and conveniently transmitting at very bright power at 123 megahertz. So we took some spectral data at the main base and also at our site. And you can see the transmission line at 123 is very booming bright at the main base. And you can still see it at our site behind the hill, but it's down by about 60 dB or so. So that gives you a benchmark for how much shielding that we get from the hill. So I should clarify, the amount of signal suppression is set by a combination of attenuation from the hill and also the distance. But the upshot is that 60 dB is kind of the rough ballpark number for if something is transmitted from the main base, it's attenuated by that amount by the time you get to our site. And of course, the helicopters only fly during the summer. So during the winter, it gets much quieter. Okay, so I'm just going to show 3 slides of gratuitous pictures to give you a sense of what deploying the instrument is like. These are photos from 2017 when we set up the experiment for the first time. So this is 3 weeks and 3 slides. So here we go. This is our ride. This is the SA Agulhas 2. It's an icebreaker that we take from Cape Town, and it takes about a week to get down south because they do oceanography along the way. So we arrived at the base a few days later. This is myself and our team. It's just 4 of us, so me and 3 students. And then immediately after arrived, we started by surveying RFI and looking for a site to set up the antennas. So that was the next couple of days. And then eventually, after we identified our site behind the hill, we waited for a clear weather window for our container delivery, called up our helicopter friends, and they dropped off our containers for us. So they dropped off our cargo, dropped us off, and then said goodbye, and then went 4 kilometers back to the main base and left us alone to do our work. So then we started up setting up the 100 megahertz antenna over here. And remarkably, everything worked the first time. So we got first light the next day. And even though the students look really cold and miserable, I promise you they're ecstatic to get the first spectra on the laptops. So this is really great. We're all really happy. The next day, we started setting up the 70 megahertz antenna. And remarkably, that worked on the first go as well. So we had all systems go a few days after bringing everything to site. So at this point, we were 1.5 weeks into the season with only 1.5 weeks to go before we had to pack up and go home. And during that time, we had to figure out how to robustify and mouse-proof our system. So it took us a while to figure out how to do all of that. Just one little fun detail, in case you're interested in, is the mice tend to be curious about cable penetration points. And so this is where they left most of the nibble marks. So we just wrapped this with steel wire cloth, and that seemed to have done the trick. So, and they also don't like brass scouring pads. So you stuff all the crevices with that, and then they leave you alone. So it took us a while to figure that out, but eventually we won, and the mice stopped eating our electronics. So that was good. We had exactly 1 afternoon to take off to go do something fun. So we went to go see the wildlife and the penguins. So that was great. Our last day of summer operations was May 4th, and then we left the next day, and that was it. So a very short 3-week season and 3 slides. And I want to give a special shout out to our winter rovers. So Kagiso Malepe was our very first inaugural winter rover in 2017. So that's him taking care of the telescope. And right now, down on the island, we have Vuli Manuka, who's taking care of it. These guys work for the South African Space Agency, and their primary job is to take care of their instrumentation. Well, once in a while, we borrow them for our instruments, and so we have them to thank for keeping everything up and running and happy.
What's the population of the base?
During the winter, it's a little over 20, so kind of 24, 25 or so. Yeah, not very many.
So you're taking data all through the winter?
That's right, yeah. So about once every week or so, these guys go, Vuli, yeah, right, that's right. So you go up there, pop fuel into the generator, charge the batteries, and then take the data out, and yeah, rinse and repeat. Okay, so that's the experiment. So let me show you some preliminary data. Yeah, spoilers, I don't have residuals to show today, unfortunately, so we're still working on the analysis. But I will show you just raw data from the instrument to give you a sense of what we're seeing so far. So this is typical raw spectra from the instruments. So this is, I can't remember which antenna it is, but one polarization and the other polarization. And there are several lines plotted on here. So the yellow is the antenna data, so that's spectra taken from the sky. And then the other colored lines are from the various calibrators. The noise source is not included in this because this is 2017 data. So in the yellow curves from the sky, you can see the falling spectrum of the galaxy. So I'm going to zoom in on that a little bit more and show you that in more detail. So this is a typical spectrum from 70 megahertz, one of the polarizations. And this is daytime data. So there's a couple of features that I'm going to draw your attention to. Is during the daytime, you can see that there's shortwave radio coming in on the left-hand side. And all of this little hash here is from handheld radios from people checking in from the huts and making sure that they're safe, talking to the main base. This bright line is from the Orbcomm satellite constellation. There's no way to get around that. So there are satellites on the sky. That's just something you have to live with. So this is daytime data, and then when you switch to night, you can see all those features go away. So I'll click back and forth a couple of times just so you can get a sense of that. So that's kind of fun to see because you can see the humans go to sleep here and the ionosphere goes to sleep here. And so all of that stuff goes away and the data become beautifully clean. So this is one spectrum, and I'll show you a waterfall plot next. So this is from the 70 megahertz antenna and 100 megahertz with the two polarizations. These are autospectra. And we have an instrument paper that was put out earlier this year, so you can see this in there. The frequency range is a little bit different for the two plots, but it's 40 to 100 up here and 70 to 130 down here. And this is about 12 hours of data, so you can see the galaxy drifting in and out of our beam. And this is completely raw, so there's been no processing and no data excision except for taking out the calibrator measurements. And you can see that there's 0 visible RFI, which is really kind of amazing from this location. So one thing you can do is apply a very light high pass filter to highlight the high frequency structures and to pull out any residual RFI and average these spectra together. So if you do that exercise and compare with similar spectra from the Karoo Desert in South Africa, this is the comparison. So the Karoo is in black, and this is one of the premier radio quiet sites in the world. So this is where Meerkat is operating from. It's where SKA Phase 1 will be. Hera is there. Cat 7 is there. It is beautifully radio quiet, but it is just difficult to run away from FM radio emissions. So you can see there is still a little bit of hash in the FM band. In comparison to Marion, there is just nothing at all except for Orbcomm. So we think this is a really promising site for future low-frequency observations. And yeah, unfortunately, I don't have more data to show you today from this particular experiment, but stay tuned. We're hoping to have more analysis results soon.
Why is the baseline wiggly? Is that just noise?
Yeah, so these little ripples, that's leftover systematic errors from the instruments. So there are reflections, standing wave inside the cables. And we've done a little bit of filtering to get rid of that, but there's still some left. So that's some of the work that's in progress because you want to calibrate all that out.
So there are other isolated islands in the world.
Yeah.
But this has the advantage that it only has a base on it.
That's right, yeah. So it's a balance of isolation and logistics. So.
And it's saw that one, I saw that.
That's right, yeah. So a lot of things kind of all come together. Okay, so that's this experiment, and for the rest of my time, I want to talk about a new direction that we're thinking of expanding in. So I'm going to go back to this slide and just point out that most of the experiments are kind of operating in this range, trying to focus on the absorption feature from the first stars, and also to some extent the positive emission feature from reionization. But there's this other feature down here, which comes from the dark ages, and the question is what lurks down there? And it's a pretty difficult measurement to make because you're starting to dig into where the ionosphere really causes you problems and cuts off. But this is still pretty interesting to try. So Marion seems like a pretty good site, so might as well give it a shot and see how well we can do. And the ultimate dream would be if we could possibly one day image the fluctuations down here, that could be a tremendous source of additional cosmological information and allow us to access a lot more modes. So again, that's kind of the distant pipe dream for the future, but it doesn't stop us from giving it a try. So that's what we're going to do. So let me tell you about the state of the art at these super low frequencies. So these are a representative set of some of the experiments. This is not comprehensive, but I've pinned it on one end by the lowest frequencies and on the other end by kind of the highest resolutions that we have at these sorts of characteristic wavelengths. So the record holder for low frequencies is set by Reber himself in the 60s. So that's the state of the art at low frequencies. We haven't done much better than that. So his measurements were at 2.1 megahertz, and the resolution is kind of 5-10 degrees or so on the sky. So not great, but he did manage to get glimpses of the sky. I recommend reading the original papers. They are really wonderful to look at.
This is ground-based?
Yeah, that's right, yeah. So
you get the plasma frequency is like 10 megahertz. How do you get around that?
So it depends on where you are and where you are in the solar cycle. So he was observing during a particularly deep solar minimum. And so it was not perfect. It was just, a few, I don't remember how much data he got. It was not continuous observations. It was kind of just a couple of glimpses. So, but yeah, check out his paper for details because it's, yeah, he did manage to see just a little bit. And actually, I think a little bit lower than 2.1 as well, but not much. So he holds the record. There is a satellite that operated at 4.7 megahertz, and so that also got very low resolution maps. In terms of the highest resolution maps at these frequencies, I think those are set by the DRAO 22 megahertz map. That's at 1.1 to 1.7 degree resolution. And then most recently, the LWA put out these beautiful maps going down to 36.5 megahertz with 15 arc-minute resolution. They are absolutely stunning images. But there's not a whole lot in between, so there's a lot of space for these measurements to be improved. So we're thinking of giving this a try. So of course, the first question is how low can we go before the ionosphere kills us? And these are predictions from the IRI model. So this is the International Reference Ionosphere model. And these model predictions are for Marian and Yellow, Dome C from Antarctica, and then Hobart, which is where Reber was doing his measurements. And you can see that during the solar minima at nights, the plasma frequency goes down to about 1.5 megahertz for Marian Island. And of course, this is just a model, so take it with a grain of salt, but at least it gives us some confidence that maybe it's worth giving a try. So that's what we're going to do, is that we're renewed to continue our experimental efforts through 2020. And so what we would like to do is start to try imaging the sky at these low frequencies. So in order to do that, you want multiple antennas. And in order to support multiple antennas, you need multiple observing sites. So on Marian, conveniently, there are huts around the perimeter of the island. And so this is where the seal counters and the penguin counters hang out overnight when they're going on their round island circuits. And conveniently, you can see that these huts are in a ring configuration, which is one of the classic layouts for imaging. So if you install antennas at all of these huts and calculate the synthesized beam, this is the answer that you get. So about 8 arc minutes at 5 megahertz. And since we're looking at really low frequencies, kind of 10, 20-ish megahertz or below, at those frequencies, you can conceivably write the baseband to disk and correlate afterwards. So you don't need to cable everything together. You can just operate these antennas independently if you manage to build everything in time. So that's the dream. That's the game plan. And because I burned far too many CPU cycles on coming up with stupid acronyms, this is my name for it. It's Albatross, or Array of Long Baseline Antennas for taking radio observations from the sub-Antarctic. So this is the game plan, and this is what we want to achieve in the very distant future. This past April, we installed a couple of antennas as pathfinders. So that's our exploratory gizmo on the ground, or albatross egg. So we've got 2 new antennas that we've installed on site. So these are our old PRIZM antennas, and then these are the 2 new ones that we've installed as of this past April. These are LWA antennas, so I think that's on the next slide. Oh, actually, I'll come back to that in a second, but this is a schematic. It's very simple, so we just have the 2 antennas, 2 polarizations apiece. There's some amplification on the front end, and then we pipe them into our back end, where the most important part is this piece, where we're calculating the full correlation between everything. So for our long-term plan, we want to operate these antennas independently as autonomous stations, but right now we're still doing direct correlation just to get a glimpse of what's out there and to get a feel for what we can see on the sky. So this is what we have in the field right now. Okay, so the hardware that we're using are LWA antennas. So these are just, you can buy them off the shelf. And they're spec'd to 5 to 90 megahertz frequency operation. So we're operating them a little out of spec, but it's okay. We just kind of want to see what we can see. These are basically omnidirectional antennas, and this is their beam pattern that you can get from their website. There's front-end amplification, so these are active balons on the fronts of the antennas. You just pop off the lid, and that's there. And then for the back-end electronics, we're using a snapboard again, this time using the onboard ADCs. So the specs are a little bit different. So the spectra that we're calculating are between 0 and 125 megahertz with 2048 channels, and then using the onboard native rate of 250 megasamples per second. So not too much more to say about this. The power draws, again, very low, so about 45 watts. And then this whole enclosure can fit inside a backpack, so if you want to schlep it out to a remote site and take spectra, you can. All right, so this is the thing I want to show you. This is preliminary data from our antennas that we've installed. This is a waterfall plot showing autospectra from just one of the polarizations. And you can see that the galaxy is coming in and out, and there's some shortwave coming in and out here as well. But there's pretty clear signal down to 20-ish or so without too much trouble. And then the really fun thing is I can show you fringes from 2 of the polarizations that are cross-correlated together. So this is about 3 days of data, and you can see that there is repeatable sky signal that we're getting all the way down to 10, 15 megahertz without any effort. So this is raw. Again, no cuts, no processing. This is straight from the data acquisition system onto the screen. So with no effort, we can get down to 10, 15 megahertz and see sky signal down there. And so with maybe a little bit of non-zero effort, maybe we can start to dig down here and see what signal comes through.
Is that RFI or is that the ionosphere?
A combination of both, probably. So the cruft that you see is the shortwave coming in and out. So when it gets quiet, the question is there any residual sky signal there? And we have not had the time to look yet. So it's, yeah, but it should be fun. And we've got a student looking at it right now. So that's what we're aiming for in the future. And then, so this is the R&D that's in progress for these autonomous stations that we want to develop. So there's a lot of work that needs to be done. We need to change the data acquisition, first of all. So we need to develop the firmware to write the baseband to disk, figure out a data storage plan, because the data volume is going to go up. When we operate autonomously, we'll have to figure out a solar power solution because it's no longer going to be feasible to send a human out to recharge batteries with petrol every time. There's mechanical considerations that we have to figure out. So we want to deploy these antennas rapidly to these huts and get everything up and running quickly. And you can see that the huts are not always the most accessible or friendly locations to operate from. So I deliberately picked the most, I think this is one of the most inaccessible huts. It's in a ravine. So we would like to make sure that our antenna design is simple enough that we could deploy it here if we absolutely wanted to. So this is all work in progress, and hopefully we'll have more to say about that soon. In parallel with our plans to take over the entire island on Marion, we're also thinking about expanding up north. So it turns out that there's a lot of empty space in our backyard in Canada. And in particular, McGill operates an Arctic research station that's all the way up here. And that's probably pretty quiet, is my guess. So I've just submitted a proposal to put some antennas up there and do some RFI surveying. So if anyone is interested in coming up there with me, let me know. It should be a lot of fun. Okay, so I'm going to end there and just summarize by saying that there's a lot of uncharted territory in the universe's history that we're starting to explore with redshifted 21 centimeter observations. And PRIZM is a new experiment in the global 21 centimeter scene. So we're a little less than 2 years old now, and we're looking to weigh in on the detection from edges. So the first science run started in 2017, and we're still continuing to operate right now. And we've got these new low frequency pathfinder antennas that we're just starting to look at the moment, and we're hoping to install some more in the future. So I'll also end with a shameless advertisement, which is that we are desperately looking for postdocs at McGill right now. So if you know of anyone who's interested in working on this sort of stuff or all the other research that we do, please drop me a line and please apply. So thanks a lot. I'll take questions.
Estimate your sensitivity compared with edges, or?
No, well, it's all dominated by systematic errors, right? So the statistical sensitivity, it's I haven't even bothered with the calculation to comparing the two, right?
Comment roughly how the backgrounds compare the two sites.
Oh, you mean the RFI?
Yeah.
Oh, it's definitely cleaner from Marion. So I would say that the Western Australia, where Edges operates from, is cleaner than the Karoo, but you can still see some FM lines in there. So yeah, if you're interested, I think I have an RFI plot from Raul that I can show you later on.
I think they cut half their data in the FM band or something.
Yeah, I know that they have an RFI occupancy plot in their paper, and if you look at that, their signal detection kind of butts up right against where the occupancy drops or increases. I mean.
As you continue to collect data, there's no. I mean, you understand the systematics better, but there's no statistical improvement in that.
That's right, yeah. It's all about repeating the measurement under different circumstances to get a better handle on the systematics. So there's, yeah, in some sense, there's no upper bound on that. So you just have, like Edges has been going for 10 years, right? So just gradually understanding their instrument one piece at a time.
So really that Edges paper was the fruit of 10 years of data taking?
In some sense, Because, well, their original instrument operated at higher frequencies because they were focusing on the reionization emission feature. So it's not quite fair to say that it's all that effort going into one paper, but it is building on a lot of experience that they've laid down.
Are you going to have a similar timescale?
I hope it will be less. I mean, one of the great things about EDGES is that they have posted all of their internal memos online, which sets a great model for the rest of the experiments so that we don't have to reinvent the wheel. But yeah, Raul, who is the lead postdoc on there, has just moved to McGill, and so it's been great having him around and bouncing ideas off him. They've been, in general, they've been very open about discussing ideas and pitfalls for experimental work. So I hope that combined we will make faster progress.
Okay, well, I think given the time, we should retire to the CITA lounge and talk to Cynthia there. Let's thank
Okay.
everyone.